Hello class. This lesson we're going to learn how to use regular polygons to figure out the formula for the area of the disk, that is the region inside of a circle. First, on your own, I'd like you to try to figure out the area of this regular hexagon. It's inscribed inside the circle. You're going to write the formula in terms of S and H, where H is that distance from the center to the midpoint of one of the sides. So hopefully you saw that we have triangles here. Each triangle has an area of 1/2 S times H, 1/2 base times height. And we have 6 of them. So just multiply that by 6 and we get 3SH. A little side note, that distance H, that height, another word for that is an apothem. But in this lesson, we're just going to use the letter H or call it the height. So another way we could have written the formula is like this. What if we hadn't multiplied that 6 into 1/2? Well, why would we want to do that? If we apply the commutative property, we can get the 6 and the S grouped together. And what special quantity does that represent in our figure here? What does 6 times S represent? That represents the perimeter of the hexagon, right? There's 6 sides, each of length S. So now we have a formula for the area in terms of the perimeter of the hexagon times H over 2. Now we can generalize this to any type of regular polygon. So if we have a regular polygon Pn, where n is the number of sides, we know its area is n times the area of each triangle, right? And there's n triangles. So all we did was we replaced the, the 6 in our formula with the n. So this 6, and this is the area. So we know the area formula. That's 1/2 the side length times the height. And we're going to rearrange it again. And what does n times S sub n represent? That's just the perimeter of our n-gon. And this is the general formula. So to figure out the area of any regular polygon, it's just the perimeter times the height over 2. So we're going to use this idea to approximate the area of a circle with inscribed polygons. So first, I'm going to draw a square in the circle. So recall, to inscribe a square, you draw a diameter. And then from there, you make a perpendicular bisector of this segment. And when you draw the perpendicular bisector, it's going to cut 2 more times. That's going to give you your vertices. So there's our inscribed square. And I want us to shade the region that's in the circle, but not in the square. Now, using the same idea, we want to make an octagon, so P sub 8. How can we do that? Well, we start off the same way. We start off with the inscribed square, and then we're going to find the perpendicular bisector of each side here. And that perpendicular bisector is going to touch the circle at 2 points. And those 2 points are going to be the vertices for our octagon. So that's how we can find the ones on the top and bottom, and similar for the ones on the left and right. And here's our octagon. So which polygon has the greater area? Does the square have the greater area, or does the octagon? The octagon, right? And what if we drew a 16gon? So a polygon with 16 sides. Which one would have the bigger area? Which one's a better approximation for the area of that disk? That would be the 16gon, right? That's going to have those edges that make it closer and closer to a circle. So here's an example of a piece of a 16gon. And so in general, if we just had a polygon, a regular polygon with n sides, you know it's always going to be less than the area of the polygon with double the amount of sides. Why is that true? When we, like we said before, when we draw those extra segments in there, it's going to have a bigger area because we're adding triangles onto it. It's going to be closer and closer to the area of that circle. So now we're going to do the same idea, but now with circumscribed polygons. So polygons on the outside. So to circumscribe a square, you would once again draw a diameter. Make sure it goes through your center. Then you're going to want to draw a segment perpendicular to it. Actually, draw a little bit longer, so make it so it goes past on both sides. Okay, now we don't know exactly where it's going to hit, but if we do the same thing for a diameter that's perpendicular over here, and we repeat that process, we end up with a corner of the square. So you can repeat that process for the other two sides and find your circumscribed square. Now, how could we repeat that process but for a regular octagon? Well, we can start with our square, and then we just want to cut off the corners. So if we follow this process, we should get a regular octagon. Draw right from the center of the square to its vertices, as we have in this first diagram. Mark those points, and then draw the lines that intersect exactly one time. So make one perpendicular to the radii. And then you want to chop off those corners. And this is the final product. That's our circumscribed octagon. So which one has the greater area? Does the square have the greater area, or does the octagon now have the greater area? Well, it's the square, right? The square is the bigger area because we chopped off those corners in order to form the octagon. So which one's better to approximate the area of the circle? Hopefully you said the octagon, because it's closer to the circle, right? It doesn't have those corners like the square does. And in general, how will these areas compare? So if we take any circumscribed regular polygon, and we take the one with double the amount of sides, which one's going to be bigger? The one with less sides is going to be bigger because it's going to have more of those corners, right? And we chop them off. So the more sides for the circumscribed polygons, you're going to be closer to the area of the circle. So if we do this process with any type of polygon, so we start with at least 3 sides for a triangle, the area of the circle is going to be sandwiched in between the area of a regular polygon inscribed and a regular polygon with the same amount of sides circumscribed around that circle. So if we look here, if you zoom in, you can see P16 is the inscribed polygon, and P prime 16 is the circumscribed one along the outside. This arrow should be pointing at the purple line here, not that little space. But it doesn't really matter. We're just pointing to the shape. It doesn't have to be the side, but it looks nicer that way. Anyway, so when n gets bigger and bigger, as it gets closer to infinity, the difference of those two areas is getting smaller and smaller. The more sides we have, the closer we have to a circle. So we kind of tracked the area of a circle in between these two polygons. And since the difference between the two polygons goes to 0, since the circle's trapped in between them, if we could do this an infinite amount of times, the area of the circle is going to be the area of those two polygons. If we could draw a polygon with an infinite amount of sides. Now, I know that it's really hard to wrap your head around. This is more of a topic about limits that you're going to talk about in pre-calculus and calculus, but it's a little precursor to that. So you don't have to know this definition, just read it so you have a better understanding of what's going on in this lesson. So in particular, let's see what happens. If we figure out the areas of regular n-gons that are inscribed, here are the approximations we get. And we have a circle with radius 1, so we know that those numbers should be getting close to pi, because the area would be pi times 1 squared, which is just 1. So for an equilateral triangle, we get this number. For a square 2, pentagon, hexagon, heptagon, 100gon. Oh, look at that, 1000gon. We're getting closer and closer to pi. So the more sides we add, the better our approximation gets. So now we're going to use the formula for the area of a regular polygon to figure out the area of a circle. So as n gets really, really large, as we increase the number of sides in our polygon, like we see in this diagram, what's happening to the heights? What's the height getting really, really close to? The height, the red segment's getting really, really close to the radius here, right? The more sides, the closer it is to the radius. It's going to be a little bit short of it, but the more and more sides we add to the polygons, they get closer and closer. And what's happening to the perimeter? As we increase the number of sides, what happens to the perimeter? It gets closer and closer to the circumference of the circle. So now we're just going to take what we just discovered. So this is a rehashing of what we just talked about. We're going to plug those into our formula. So instead of the height, we're going to substitute r. Instead of perimeter, we're going to substitute circumference. And this is our formula. Now we know the formula for the area of a circle is pi r squared. So let's rewrite circumference. So instead of circumference, that's 2 pi r. So we have 1/2 of r times 2 pi r. The 1/2 and the 2's multiply to 1. You're left with pi r squared, our formula for the area of a circle. Now this is also, you see why the Greeks use the letter pi. It comes from preferred perimeter, and the pi was the Greek letter for p. And so if we could find the perimeter of a circle, which ends up being the circumference, we end up getting a formula with pi in it. So that's why the Greeks chose that letter. So now let's apply what we've learned. We want to approximate the area of this disk with radius 2 with this regular hexagon. So see if you can figure out its area, and I'll give you a hint. Think about what type of triangle we have here. It's one of our special right triangles. So hopefully you saw that we have a 30, 60, 90, right? Because we know that these are equilateral triangles. This is 90, that's 60, that's going to be 30. So if the radius is 2, this little piece right here is 1, and the longer leg is square root of 3. And now we can plug into our formula that we learned. 1/2 the perimeter times the height. So 1/2, 2 times 6 times square root of 3. Right, each side here is 2, and there's 6 of them, so that's the perimeter. And we end up with 6 times the square root of 3. So how good was our approximation? We want to figure out the percent error now. So our answer was 6 times the square root of 3. What's the actual area of this circle? Well, it's pi r squared. Radius is 2, so it would be 4 pi, right? 2 squared times pi. So to calculate the percent error, we take our approximation, and we subtract the actual area from it. Take the absolute value and divide that by the actual area, multiply by 100%. So we plug in here. We really should have the absolute value over here. Subtract those two numbers and divide by that, and we get about 17.3%. So it's kind of a big percent error, but the more and more sides we add, the smaller and smaller that percent error we'll get. This lesson we learned how to use regular polygons to figure out the formula for the area of a disk. Thank you for watching this video.